this chapter, we're going to learn about inductive reasoning and how to use it. We're also going to learn to differentiate it from deductive reasoning. So first we need some definitions here of some terms. The first term is conjecture, and a conjecture is an unproven statement that is based on observation. Notice, unproven statement based on observation. Inductive reasoning is a process that includes looking for patterns and making conjectures. So when you're looking at patterns and from those patterns you draw some kind of conclusion or some statement, that is your conjecture. So for example, in this picture here, I'm looking at these figures. I'm trying to identify the pattern of how, we get from figure 1 to figure 2 to figure 3, and then what might a figure 4 look like, right? And so I have to figure out what the pattern is, and then what conclusion can I make. So I'm going to be using inductive reasoning. And in this case, I notice that I start with one line and it's the upper half. Then I have 2 lines and it's the left quadrant. Then I make 3 lines, break it into 6 pieces, and it's that left upper side again. And so based on that, I think the pattern is to add a line each time. So now I'm going to have 4 lines. And I'm going to shade in the side on this left side, right above this middle. I notice that it's here, it's here, it's here. So I'm going to do it there as well. And so that's what I think figure 4 would look like. But again, that's a conjecture. It's unproven, but that's definitely using inductive reasoning. I'm following the pattern and drawing a conclusion. Same thing here. They might give me numbers. And I notice that everything is going up by plus 2 cents or whatever, or 0.02, right? So I know the next number using the pattern and inductive reasoning. My conjecture is going to be that the next 3 numbers are 5.09, 5.11, and 5.13. Again, it's unproven, but based on the pattern, the observation that I see, and inductive reasoning, that's my conjecture. Now, sometimes we're going to get some information and we're going to make a conjecture, right? And then we have to test our conjecture. So if I have such, for example, numbers such as 3, 4, and 5, these are called consecutive integers. They want me to make and test a conjecture about the sum of any 3 consecutive numbers. So I might start by saying the sum is 12 here, right? Well, let me then do maybe 6, 7, and 8. And I'm going to get that my new sum is 21. And I might even do 9, 10, and 11. And I get 30. And so I notice, wow, maybe my conjecture is that when I add them up, notice that the product is, the sum is 3 times the middle number. Notice 7 times 3, notice 10 times 3. Now that might be, right? So the sum equals 3 times the middle number. That's one conjecture. Maybe somebody else said, oh, I noticed that when I subtract, it's always minus 9 or 9 more than the one before it. So maybe each sum is plus 9 the one before. Okay, so now what I want to do, though, if I'm going to test my conjecture, what I'm going to look to see is I'm going to try a bunch of numbers and make sure that it works every time. And when I try numbers, you want to try numbers like negative numbers, maybe -1, 0, and +1. That adds up to 0, and guess what? 3 times 0 is 0. This one's looking good, right? Maybe 100, 101, and 102. And that's going to equal 303. And guess what? It's times 3. It works, right? Or 330. Or 303, sorry. So this one, I'm not really able to find one that doesn't work for this one. This one here, notice that if I do, if I add them, 100, 101, and 102, well, let me try to find a something that doesn't work, right? Well, maybe, I guess if I did the 97, 98, and 99, I get I get 294, and notice that it is -9 or +9 in the other direction. So guess what? I think this other conjecture might be, but it's +9 the one before it if I go in consecutive order, like this is 97, so the other one's 96, 95, 94. So I found my conjectures. I did some conjectures. It just happens to be that I think both my conjectures are correct because I'm not able to find an example where it's not correct. Okay? What I'm trying to do when I look for those examples where it's not correct is to find a counterexample, and that's what I'm really doing. I'm trying to find that the conjecture is false or prove that it's false by providing just one example for which it doesn't work or is false. If I'm able to do that and I can just find one example that makes it false, then the entire conclusion is false. Then my conjecture is false, okay? But I have to constantly be seeking this counterexample. So, for example, if you live in Florida, then you live in Miami. Well, yes, if you live in Miami, you do live in Florida. But however, what if you live in Davie? I live in Davie. Guess what? I also live in Florida. So this is a false conclusion because I was able to find a counterexample of how I can live in Florida, yet not in Miami. So this is also what you would do in those sometimes, always, and never questions. Before you say never, before you say always, or sometimes, you want to try to find that counterexample. You want to find the one that, makes never a false statement or makes always a false statement. So again, if I ask you to finding in the tests or whatever, if I ask you to find counterexamples, a student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. So the conjecture says the sum of two numbers is always more than the greater number. So the sum of two numbers is always more than the greater number. So 2 plus 3 is 5. Notice 5 is greater than 3. So far my conjecture appears to be true. And so if you use normal positive numbers, it's probably going to be true, right? Because we got to think a little bit outside the box. If I do 100 plus 99 is 199, and 199 is greater than 100, and so this is true as well. So now let's stop thinking inside the box and let's think a little more outside the box. Let's think of numbers. Whenever you're trying to prove something, think of fractions, negatives, and 0. So let's try fractions first. 1/2 plus 3/4 equals 1 1/4. And 1 1/4 is greater than 3/4. And so when I used fractions, guess what? This still worked. Let's try 0. 5 plus 0 is 5. Well, guess what? 5, the sum, is not greater than 5, the biggest number, right? It's not. So I just found a counterexample. When you add something to 0, the sum is not greater than the greater number. It's equal to the greater number. And so here's my counterexample. 5 plus 0 is a counter. Another counterexample could have been, most likely, -3 plus 5 equals +2. 2 is less than the greater number. So guess what? This does not work either. So another counterexample would have involved adding with a negative number. And so again, always think outside the box. Anybody can do 1 plus 2, 5 plus 7, but you have to think fractions, think 0, think negative numbers. So now that we've done inductive reasoning, where again, based on observations and patterns, we draw a conclusion, but it's unproven, deductive reasoning actually uses facts, definitions, accepted properties, postulates, theorems, and the laws of logic to form a logical argument. So basically, we reason things out, but these aren't unproven things. We're using real things, that definitions and facts. We're not just making an unproven conjecture or conclusion. So within deductive reasoning, we have two types of laws of logic. We've got the law of detachment, and we have the law of syllogism. The law of detachment basically says that if the hypothesis of a true conditional statement is true, then the conclusion is also true. So basically what's happening is you're given this first statement. If it is Friday, then I eat pizza. My hypothesis is if it's Friday, my conclusion is I eat pizza, and I'm told that this is a true statement, okay? This is a fact. So then, in another statement, I'm told that it is currently Friday. Basically, being Friday is the P part or the hypothesis part of this true statement above. So if it's Friday, if I'm given P again, then I can logically conclude Q, because they set the tone right there. They set that if-then statement in the beginning, and if this follows it, then the conclusion is also true. So if it's Friday, then I'll eat pizza today. And that's a fact, because again, and it's a logical conclusion, because I was told that that's what happens when it's Friday. I'll show you other examples where it might not be. For example, maybe they'll give you the same problem. They'll give you this P here, this PQ. If it's Friday, I eat pizza. But then they'll tell you, I ate pizza today. And somebody will say, oh, well, if you ate pizza, then it's Friday. And that's not the same thing, okay? Because if I eat pizza today, it doesn't necessarily have to be Friday. I can eat, if it's Friday, I eat pizza. But I might eat pizza on Tuesday. And so it has to be given to me in the same order. I have to be given a PQ and then given P. And if that happens, then I can conclude Q logically. That's what law of detachment says. The law of syllogism is one that you've seen in the transitive property in mathematics. This one says, if P, then Q. And then it gives you another statement where the hypothesis, notice that in the first one, the hypothesis was P, the conclusion was Q. In the second sentence, I'm given if Q, then R. So the conclusion of one, right here, becomes the hypothesis of the other. And when that happens, you can bypass that and just say, well then, if P, then R. Okay, so again, that's the if P, then R. So how does that work with a sentence? Think of this. If I say, if it's an apple, then it's a fruit. Then I say, if it's a fruit, right, here's my second conditional, then it's healthy. So notice that I had if P, then Q. P is apple, Q is fruit. Notice here I start with Q, then R. I'm saying that if it's a fruit, then it's healthy. So now using the law of syllogism, I can say if it's an apple, then it's healthy. And what I did was I went from P straight to R. I basically can cancel Q because it kind of doubled up, okay? So that's how we do law of syllogism. Same here in this example. We start out and we have if it's Friday, P, then I go to the movies, Q. So if P, then Q. If I go to the movies, notice I'm starting back up at Q, then I eat popcorn. Popcorn is R. So notice that it's if P, then Q, if Q, then R. So I can completely cancel out the Q's and go straight from if it's Friday, then I eat popcorn. And that's a valid conclusion using syllogism. So here in this example, it says here, if the measure of, this one's hard to read. So what this one's saying, if the measure of angle R is between 90 and 180, then angle R is obtuse. So if the measure falls between 90 and 180, that's your P, then angle R is obtuse. That's the Q. Then the first statement says the measure of angle R is 155, which is between 90 and 180. So they're giving you P again, which means now, so they gave you if P, then Q, and then they gave you P. Well, again, if they give you P, you can conclude Q. So what's my conclusion? Then angle R is obtuse. So it was perfect. They gave me the relationship of the conditional statement, then they gave me P, and using the law of detachment, I can conclude Q, that it is obtuse. Here we have another example. Now this example here says we've got, if Janelle gets a job, then she can afford a car. And then we have a second scenario, if Janelle can afford a car, then she will drive to school. So what they ended up giving us here was if P, then Q. So if P, then Q. The P part in the initial is Janelle getting a job. Q is she can afford a car. So she can afford a car is the conclusion in the first one. But now notice that in the second one, if she can afford the car is now the hypothesis. And so if she can afford a car, then she will drive to school, and that's your new conclusion. So what happens is, notice we have if P then Q, if Q then R, and when that happens, when the same thing, she can afford the car, is a conclusion and a hypothesis, then I can go straight from P to R and say if P, then R, which means the statement that I can make using the law of syllogism is if Janelle gets a job, then she will drive to school. So basically, I've got here, if Janelle gets a job, whoops, don't want to do that. And then in green, the R. So I went from P to R and completely bypassed the Q's, which sort of like cancel out. So here it says, state the law of logic that is illustrated. So again, I got to look at what's happening here. It says, if you get an A on your math test, then you can go to the movies. Then the next one says, if you go to the movies, then you can watch your favorite actors. So once again, I started with a P to Q, and then I go from Q all the way over to an R. So if P, then Q, if Q, then R. And so that's kind of the setup. And then now the statement is if you get an A on your math test, if you get an A, then you can watch your favorite actor. And so now you realize, oh, this is a P to R situation. If P, then R. And so this is the law of syllogism. Here we come to another one, and it says, again in this one, if x is greater than 12, then x plus 9 is greater than 20. So here's my P, here's my Q. So if P, then Q. Now I have a second statement here, and the second statement says, so this is my biconditional that sets the relationship, and then now they tell me that the value of x is 14. Well, if x is 14, that means x is greater than 12, so they're giving me P. If x equals 14, they're giving me the P part, and therefore, notice that they're concluding Q. They're saying, well then Q, x plus 9 is greater than 20. Is that valid? Yes, because they gave me the biconditional, and then they gave me the first hypothesis, and now I can make this conclusion that this is true. And so this is the law of detachment. And lastly, decide whether inductive or deductive reasoning is being used to reach the conclusion. Here we have each time Monica kicks the ball up in the air, it returns to the ground. So the next time Monica kicks the ball up in the air, it will return to the ground. Now this is based on observation. And when it's based on observation, it is inductive reasoning. So what happened is they observed it, they found a pattern, and they made a conjecture. And so this would be an inductive reasoning problem. This one here that's talking about reptiles being cold-blooded and all of this is definitely a deductive reasoning problem. This is not something based on some type of observation. But it's also not really following any of the laws of syllogism that we learned earlier. Notice all reptiles are cold-blooded, so if P, then Q. So what they're saying is if it's a reptile, then it's cold-blooded. The next sentence says parrots are not cold-blooded. So now we have some new scenario, right? So you start to wonder, okay, well, how do I do that? Parrots are not cold-blooded. And then it says Sue's pet parrot is not a reptile. So there's a lot going on here. This is assuming, if not cold-blooded, then it's not a reptile, is what we're really trying to get to here. So it says all reptiles are cold-blooded. And then this says parrots are not cold-blooded, and so Sue's pet parrot is not a reptile. So we kind of started with if P then Q, and we went over here to the contrapositive of it. We ended up in the contrapositive saying, well, if not Q then P. Remember, the contrapositive is the inverse and the converse together. The inverse negates it, and the converse swaps it. And so this is logic, but again, it doesn't really follow the law of syllogism, and it also doesn't follow the law of detachment, but it is deductive reasoning.